In this section, we're going to continue our talk on optimization, except now we're going to be doing our optimization problems involving modeling and applications. Note that this is usually one of the tougher topics in this course, and the reason why it's so tough is because we have to translate this word problem into a problem that we did in section 4.2. Once we are able to do that, then we follow the same steps as we did before. We're going to try to go through this step by step and try to show carefully how we're going to do each problem, and we'll talk about why this can be a difficult section. So in this section, again, we're going to be doing the same kind of global extrema kind of problems, finding the minimum and maxima, but we're going to apply it to problems in geometry and modeling and kind of do a wide array of different problems we're going to do. So here's our steps we're going to look at. I've broken this down into a 7-step kind of thing, and we'll try to go through it slowly in the first example and then a little bit faster in the second, and we'll do a bunch of practice problems in the next video. So first of all, when we are asked to minimize or maximize something or optimize something, then we are trying to find the global minimum or global maximum of some function. And it's important to know this at the very beginning, that what are we doing in this section? We are trying to find a global min or a global max of a function, which means that we're going to be finding critical points, which means that if we have a closed and bounded domain, that we're going to be plugging in those critical points into the function, seeing which one is biggest, which one is smallest. If we don't have a closed and bounded domain, then we're going to have to do some more work on the looking at the limits and testing the points using the first derivative test or second derivative test. That's what we did in section 4.2. So here's our steps. The first one is, I think, probably the hardest step of the whole kind of problem, and that is we need to draw a picture, assign variables, and really just understand what the question is asking. This is translating the problem into something that we can understand. Drawing a picture could mean a lot of different things. In some problems, we won't be able to draw a picture. We'll see that in the second example that we do today. But in most of the time we can. Assigning variables is very important. And again, just understand in general what's going on. The next step is identify the quantity that's going to be minimized, maximized, optimized, and we're going to write it as a function. So we might be trying to maximize area. We're going to identify area and try to write it as a function. We might be trying to minimize cost, and we're going to try to write cost as a function. When we do this, we're probably going to have the function be written in terms of more than one variable. We're going to have area equals length times width. And that's going to be an issue when we try to deal with these functions, is we don't know how to deal with functions in two variables, so we need to translate that into a function of one variable. Once I have identified that function and written it out in terms of probably more than one variable, then we are going to try to do the process of translating that function into a function of one variable. That is, we're going to find a constraint equation that relates the other variables together. So if we have length and width, we're going to try to find some kind of equation given in the problem that will relate length and width together. Maybe length is twice the width or something like that. And then we're going to use that constraint equation to rewrite the function in terms of one variable. And this is all boiling down to our first big step. This is how we find f of x. These 3 steps, we are trying to find f of x, our function that we're trying to minimize or maximize. So step 1, understand the question. Steps 2 through 4, find the function. Step 5 is going to be finding the domain of the function in the context of the problem, which is almost certainly going to be different than the domain of the function just in general. Note that we are hoping that we can find a closed and bounded domain, because that makes our problems easier to do. So in this step, I think the best way of going about it is, if our variable is x, or whatever our variable is, we're going to be asking what's the largest value that variable can be in the problem. And we're going to ask what's the smallest value the variable can be in the problem. And when we're doing that, one of those questions is probably going to be very straightforward, and the other is going to be more difficult to answer. And we'll see that in our examples when we do it. So maybe finding the largest value is going to be fairly straightforward. Finding the smallest value might be weird. So the other way to do that is it's often equivalent to asking how large the other variable can be. And we'll see an example of that in our first example. All right, once we have that, this is all to try to find the domain. And after step 5 here, we have now translated this question into a section 4.2 problem. We have a function, we have a domain, find the global min or global max of the function. And that's section 4.2. Finally, there should be one more step at the end, and that is put your answer in terms of the context of the problem. Make sure it makes sense. Add units to the end of your answer. Whatever it is, just kind of sum it up and make sure it all works out. All right, let's go step by step through our first example problem, which is a pretty classic kind of optimization problem. In fact, it's one that you may have seen in a pre-calc course as well, because you are able to do it using facts about quadratic functions. All right, so a farmer has 500 yards of fencing with which to fence 3 sides of a field. A straight river will form the 4th side, so no fence is needed along the river. Find the dimensions of the field with the greatest area that the farmer can create. So step 1, we're going to draw a picture, assign variables, understand what the question is asking. All right, so there is a river here. It's a beautiful river. Maybe there's a little fish coming out of it. Whatever, it's a river. And we are going to build a fence that goes along and trying to find a field that fence encloses. But that fence only has 3 sides because we don't need to fence along the river. Maybe there's some cows in this field and they're not going to cross the river, so they're bounded by that river. So we're trying to find the area, we're trying to find the greatest area of this field. And the dimensions, our variables that are going to be changing here, are going to be the length and width of the fence. So maybe we'll call this variable x. That's going to be the width of the fence, or the length, whatever one you want to say. And we'll call y, the sides of the fence. Maybe that can be the length of the fence. Maybe you want to call it W and L for width and length, whatever works best for you. That doesn't really matter. And we're trying to find the biggest area here. So we've drawn a picture, we've assigned the variables x and y, that's important. And maybe we're trying to understand what the question is asking. We want to try to find the biggest area. We have different x's and y's. So maybe for this first question as well, let's try to understand the question by maybe drawing some pictures of some different fields we could have. Right, so maybe we have a really long and skinny area here. These are just coming out examples, maybe what we have. Maybe we have a really long and skinny fence like this. Maybe we have a square. And we're going to have maybe everything in between. We want to try to find what dimensions are going to give us the biggest area. Is it a long and skinny kind of field? Is it a square field? Is it something kind of in between? That's what we're trying to figure out. All right, which one of these areas would be the biggest, or is there something that I haven't drawn? We'll come back to these pictures when we think about the domain as well. All right, so identify the quantity that is being maximized or minimized and write it as a function. We are trying to find the greatest area. That means that we are trying to maximize area. And we know that area is equal to the area of a rectangle here is going to be length times width. So what we have here is area is going to be x times y. We've written our quantity as a function. The only problem is it's a function of two variables, which we said is going to happen often. And now the next two steps are going to be trying to write that as only one variable. And that is we need to find a constraint equation to relate their variables together. And that's going to be given by some information in the problem. In this case, that is the farmer has only 500 yards of fencing. Let's talk about why it's a constraint equation. If we had unlimited fencing, then this question is not very interesting. What's the largest field you can create with unlimited fencing? You can create as big of a field as you want. So without that constraint, this isn't a very interesting question. That constraint is only 500 yards. So we only have 500 yards of fencing. So in our problem, using our variables, how much fencing do we have? Well, we have two sides of length y and one side of length x. So our total fencing is going to be 2y plus x is going to be equal to 500. In fact, it's going to be just less than or equal to 500, but I think we can agree that if we want to find the biggest area possible, then we should probably use all of our fencing. If we have anything left over, then we could have created something a little bit bigger. So we want it to be equal to 500. And this is our constraint equation. All right, so now we are going to use that constraint equation to rewrite area in terms of just x or just y. So let's recall we have area equals x times y, and 2y plus x equals 500. So there's going to be one of two options here, and we'll kind of show both in this first problem. So option one, we solve for x. That is, we're going to write x is equal to 500 minus 2y, and we're going to plug that into the area equation. If area equals x times y, we're going to plug in x equals 500 minus 2y. So that's going to give us a equals 500 minus 2y times y. And note that this is a function of y. We could write it as 500y minus 2y squared. The other option is we could solve for y instead and get a function of x. So that is writing y, 2y equals 500 minus x. So y is equal to 250 minus 1/2 x when we divide by 2. So when I plug this into x times y, we get area equals x times 250 minus 1/2 x, or 250x minus 1/2 x squared. And that is going to be our function of x. So either way you do it, it really doesn't matter. There's positives and negatives of both. Maybe the positive of option one is we don't have a fraction to deal with. The positive for option two is we have x, and that's familiar, so that might be nice. The negative for option 1 is, again, we don't have x. We have to deal with fractions for option 2. It really doesn't matter which way we go. To try to get more comfortable with not dealing with x, we're going to use option 1. We're going to have this function. So we're going to try to minimize or maximize that function, find the global min or global max of that function on some interval. What is that interval? That's our next step, find the domain. And that's going to be asking, what is the largest value y can be, and what's the smallest value y can be in context of the problem. And I would say one of those questions is easier than the other. In this case, I think the easier question is, what's the smallest value y could be? I think the answer is 0, or at least very close to 0. And here's where we're going to do something kind of weird as well. Let's think about, what does a field look like with y equal 0? We have our river. We have y equals 0, so we just have a fence with x with no y. And this is what I'm going to call a very stupid field. And the area of that field is going to be 0. But anything greater than 0 will give us a little bit of area to deal with. And it can't be less than 0, doesn't make any sense. So that's going to be the smallest value it can be. The largest value y can be is a much more difficult question to answer. It's not that difficult, but it's more difficult. But it's easier to answer by asking, what is the smallest value x can be, the other variable? And that answer is 0 for the same reasons as below. So then we have our constraint equation that we have 2y plus x equals 500. So if the smallest value of x is 0, that means y has to be as big as possible. We plug in 0 into this constraint equation, and we get y is equal to 250. Now, you may have been able to figure that out on your own without that extra help, but that's going to be kind of a nice way to get around it. Note that this is also a very stupid field. We have kind of two fences, one on top of the other, with an area of 0. So there are two options here. We have our domain for y is going to be parentheses 0 to 250, or we have bracket 0 to 250, noting that y equals 0 and y equals 250 give a stupid field of area equal to 0. Now, I think if it didn't matter if I had closed or open domains, I would pick parentheses 0 to 250. That's a little bit nicer to deal with. But since it really is nicer to have a closed and bounded domain, it is going to be much nicer to do bracket 0 to bracket 250. We can use the extreme value theorem now. So let's now use our function and our domain and now answer the question. So we have f of y equals, it's going to be 500y minus 2y squared on the domain 0 to 250. So we're going to find our critical points, That is, find the derivative, which is going to be 500 minus 4y. Set this equal to 0. 500 equals 4y. It's going to be y is equal to 125. We also need to find when the derivative is equal to, or derivative doesn't exist. That's at endpoints 0 and 250. And then we just need to plug those into the function. We have f of 0, f of 250. Note that we already found that both these are going to be 0. That's our stupid field that we have, which means that this 125 is going to probably be our maximum. Right? We plug in 125 into our function. That's 500 times 125 minus 2 times 125 squared. Or if we think about this as x times y, we have a 125 here, a 125 here, which means that x has to be 250. Either way, it's going to be 250 times 125, which is equal to 31,250. So we have a global max of 31,250 at y equals 125. And note that where did I get this 250 from for x? That was y is 500 or 250 minus 1/2 x, or 500 equals 2y plus x. So if y is 125, sorry, I should write this as x. We have x is equal to 500 minus 2y. 500 minus 2 times 125 is 250. And that's going to be our x value here, which is going to be important. So that's basically the answer to our question. Now let's just put the answer in terms of the context of the problem and make sure it makes sense. So let's go back to the original problem real quick. It says, find the dimensions of the field with the greatest area that the farmer can make. That's what we're actually asking in this question. So the dimensions for the greatest field are going to be 125 yards by 250 yards. We have a field that's going to look like this. 125 yards by 250. And we don't even ask for what is the biggest area, just what are the dimensions of the area that'll work. And this makes sense in the problem. We have 500 feet, 125 plus 125 plus 250 is 500. This looks like this could be, the biggest area that we might have. If we look at the function in terms of the area, here we actually had it with x, right? Or sorry, this was a of y here. We called it y instead of x. We have when y was equal to 125, we had the biggest area, 31,250. We had that as a local max or global max. And at 0 and 250, we had an area of 0. So each problem that we do is going to be following those steps. And these can be lengthy problems. And unfortunately, each problem can be wildly different than other problems on the first few steps. As we get through the problem, once we get to kind of step 6, it's going to be the same sort of thing as we've done in section 4.2, but it's different for each problem before then. Let's do another example in this video, and then we'll do a bunch of practice problems in the next video. So wildly different problem here. Find two numbers differing by 42 whose product is as small as possible. So step 1, draw a picture if possible, which is not possible in this problem really, and assign variables. So let's call x our first number, and let's call y our second number. Let's try to understand what's going on. We want to find two numbers that are differing by 42, that when I multiply them together, I get the smallest number possible. So step 1, not much to do. Step 2, I want to minimize here the product. So I'm trying to minimize x times y. Step 3, what's the constraint that I have? Well, I have that these numbers have to be differing by 42. Without that, then this question is not very interesting. So I need that when I have, let's have x be the larger number, y is going to be the smaller number. So here I'm going to have x minus y is going to be equal to 42. Step 4, I am going to rewrite the product in terms of one variable. Here I think it might be easier to write it as this equation as x equals 42 plus y. We'll keep everything positive. So then our product here is 42 plus y times y, or 42y plus y squared. And we'll call this our function of y. That's what we're going to try to minimize. Step 5, we have to find our domain. So we want to find out what is the largest value y can be. And the smallest value of y. And there really is no bounds here. We have any number could do the trick. So we're going to have to do some kind of work on this problem past that. All right, we can have negative numbers, we can have positive numbers. Those numbers just have to differ by 42. All right, so step 6, now we have find the global minimum of f of y equals 42y plus y squared on the interval negative infinity to infinity. So we're going to find the critical points by finding the derivative. That's going to be 42 plus 2y. Set this equal to 0. It's going to be a 2y equals negative 42. Y is going to be equal to negative 21. That is a critical point. When does the derivative not exist? There's no points, nothing to consider here. So we have one critical point, and it might be tempting to just say that's our answer. When y equals negative 21, that's going to be where we have a global min. But we do need to check whether that is a global min. And let's use the second derivative test to do this. The second derivative here is easy to find. It's going to be just 2. That's greater than 0. So this is going to be so at y equals negative 21, we have a local min. And since we only have one critical point, we have a local min, we have a quadratic function, it's going to go off in both directions. I think that's enough work to kind of show that step 7 when y equals negative 21, and note that that's going to be x minus negative 21 equals 42. That's going to be x is equal to 21. There's our two numbers with the smallest possible product. So without the closed and bounded domain, there's a little bit more work we have to do. In this case, we just need to test whether it is a local min. We could do some work about limits as well, but I think that's enough work to show in this problem. And that's going to be kind of familiar in problems like this. Again, the hard part of these problems is not so much steps 6 and 7. It's really steps 1 through 5. Find the function, find the domain, and then we can go from there. We'll go over some practice problems in the next video that are going to look much different than the two that we did here. So look forward to that.